Okay, welcome everybody. Good to have a
Got a bit of an echo there. Don't know if
echo of somebody. Please go on mute, everybody who's not speaking. So welcome to the meetup. We got two parts today. We have Rami and Pramod are going to kick it off, talking about Kafka streaming and taking advantage of event-driven serverless architecture using Kafka, bringing agility to workflows by lessening infrastructure management. And then Ben's going to come in, Ben Farr, in about 30 minutes, and he's going to talk about Azure DevOps and OpenShift. Azure DevOps is getting a lot of um, movement and adoption in the market. So we're going to talk, or Ben's going to talk about three patterns that you can apply to build pipelines for OpenShift deployments with Azure DevOps. So I'm going to hand over now to Pramod, who's going to kick it off.
Pramod, you're on mute.
Am I audible now?
Perfect.
All right, cool. Thank you. All right, cool. Thanks. So what I'll do is, in this presentation, we'll actually give you a walkthrough of Apache Kafka in the beginning, and then my friend Rami will actually give you details on serverless concepts as well. After that, we'll actually give you a demo, which is actually a recorded version of things due to time constraint. Then if we have time, then we'll actually go to some of the Q&As as well. All right. So for those who don't know what Red Hat AMQ is, let me kind of give you a quick introduction of what it is. Over the years, Red Hat AMQ has evolved and is based on three main projects, namely Apache Kafka, Artemis, and Interconnect. In this presentation, we'll mainly focus on Apache Kafka Broker. So let's start with the question, what is Apache Kafka? Kafka is a streaming platform which actually helps us in storing, delivering, and processing the data. This makes it an ideal candidate for doing event-driven architecture. And it also has a pub/sub system as well. Hence, it can actually be used as an alternative for doing traditional messaging system as well. This Kafka was actually developed in LinkedIn back in 2010, and then later was actually open sourced in 2011. Kafka is designed to be fast, scalable, durable, and available. All of this data is actually partitioned. This is one of the ways how it actually kind of achieves high throughput and low latency. So Kafka is an ecosystem, right? So why am I saying it as an ecosystem rather than saying it as a streaming system, right? The reason why I'm saying that is because Kafka actually provides its own client libraries for different languages, and it has Mirror Maker, and it has Kafka Connect. It has a lot of third-party tools, like, for example, for big data, you have something plugins for Spark and things like that. And hence, Kafka is not just a streaming system, but an ecosystem of many different components as well. So let's look at the deployment options of AMQ streams, which is based on Kafka. AMQ streams can be deployed on VMs and as well as on containers. If it's deployed on VMs, then it kind of follows the standard installation and working model. But when it's deployed on containers, then the same standard set of installation cannot be used. The reason is because in Kubernetes, one needs to understand the working of Kubernetes very well and then manage the configurations of Kafka themselves, right? Like, let's give you an example. For instance, Kafka needs a stable network address and a broker identity to work. Or, for instance, in Zookeeper Ensemble, each node needs the configuration of other nodes as well. So to actually achieve all those things on containers, you either need to actually create an observer pattern on your own and then do all the deployment and configuration for yourself. Or you can actually use something called a Stremzy. Stremzy is actually an open source project which actually helps us in running Kafka on Kubernetes and OpenShift. It provides container images for Apache Kafka, Zookeeper, and other components as well. It's not just that, it also provides you operators for actually doing deploying, managing, and configuring Kafka clusters. In a way, it actually helps us it provides us a Kubernetes native experience for the users. Well, let's understand why we need to use AMQ streams. Kafka was created considering scalability and performance in mind, like I said earlier. It can actually scale horizontally by adding nodes to the running cluster with minimal impact to the throughput and latency. Kafka also guarantees the order of messages. Well, this is because each partition is an ordered, immutable sequence of records that is continuously appended to. And to put it in simple terms, it's kind of, it is a structured commit log, right? And let's say if you have more partitions to achieve parallelism and also maintain the order of messages, then you can actually use some of the methods, like one of the methods is like using hashing key partition. Okay, so another advantage of Kafka is that we can actually do rewind and replay of messages if required. The amount of rewinds that we want actually have as part of the system depends on the storage of the disk. And this actually doesn't impact the performance of the system or the cluster as well. You can actually rewind it based on a specific current offset or based on a specific time or based on latest, earliest, or also based on a specific offset value as well. Okay, all of these things kind of sounds good, right? So what is the real catch in here? Proxying Kafka protocol can be very difficult. Well, it's because all the clients needs to be connected to the brokers, and client needs to actually receive the messages through a partition leader. Let's say if you have multiple partitions on multiple brokers, this kind of compounds to the existing issues as well, isn't it? So it's kind of same for load balancing as well for Kafka protocol. These things actually can be kind of solved partially by using HTTP REST proxy or using AMQP Kafka bridge. And another drawback is that Kafka is kind of a dumb broker and a smart client. One needs to really understand the architecture before using it. Like for example, let's say if you have too many partitions, and then you may either have too many brokers, or you may actually put load to per broker as well, right? Or it could be like you may have less partitions and then not enough clients to actually run the parallelism operations to things. And it's not just that, and the Kafka also kind of doesn't actually support decreasing of partitions. That's one of the reasons why we need to actually keep all those Kafka limitations and then make sure that we actually design the Kafka cluster before implementing it. Okay, now let's look at some of the use cases of Apache Kafka. Apache Kafka can be actually used for capturing data streams or events that can later be used by different systems for doing its own backend operations. Hence, it can actually be used as a data integration kind of systems. Apache Kafka can also be used for collecting logs and aggregating the metrics and logs as well, right? So which can then again later be used for doing some analysis or doing some alerting based on specific errors and things. It can also be used for tracking website activities. Kafka was mainly created for doing this in LinkedIn, where the user activities are recorded in an order in which it was actually performed. And Kafka can also be used for doing real-time processing, where like in case of AI ML implementation, where one is to actually read, process, and write streams in the real time. And it can also be used for doing AOT operations as well. These are some of the use cases for using Kafka. All right, so we have come to the last slide. I've tried to provide you some basic info on Kafka with the given time. If you want to really learn more on things, then what you can do is you can go to red.ht/try-Kafka. Thank you. Back to you, Rami.
Thanks, Pramod. I will now share my screen. Pramod, is my presentation coming in clear? Beautiful.
Yep.
So let's start with a quick reminder of what serverless computing is. So serverless computing at the end of the day boils down to building and running applications without having to worry about server management. Serverless creates a layer of abstraction over the underlying infrastructure. So this allows developers to focus on code, which improves their productivity and reduces the time to release new product features. In a serverless architecture, an application is executed to cater for a specific demand. If there's no demand, the application is scaled down to zero and no longer consumes resources. That means you get more density on your cluster because resource allocation is optimized when idle applications are scaled to zero until they are back in demand. This sounds amazing, right? So, how can we adopt a serverless architecture? Now, this is where Knative comes into play. Knative is a Kubernetes-based platform for running serverless workloads. It is an open source project that was started by Google in 2018 and is now a vibrant project on GitHub that is backed by Google, Red Hat, and many more. Knative consists of two components. The first is Knative Serving. So serving is an event-driven model that serves the container with your application and can scale it to zero. So serving is kind of the implementation of the serverless definition that we've just talked about. And the second component is called eventing. Eventing defines a common infrastructure for consuming and producing events that stimulate applications. So eventing's job is to pipe events from third-party sources into our serverless application. Let's first explore the serving component of Knative. Now, again, this is the component that gives us the ability to spin up a container and then scale it to zero after being idle for a configured period of time. In Knative, a developer interacts with a higher order concept called a Knative service. Knative service handles route creation, configuration, and revision management. Now, to implement all of that, Knative serving defines a few constructs. Now, the first are configuration and revision. Those two are heavily tied together, so configuration literally represents the configuration that is needed for an application, like the image you want to run, the environment variables you'd want to set, and things like that. And a revision is an immutable snapshot of that configuration. So every time you change the configuration, it will generate new revisions. A route implements ingress and traffic splitting. So the route in this example directs 10% of the traffic to one revision and 90% to another revision. This allows us to easily implement canary deployments and different rollout strategies in general. And on top of it all, there is a Knative service, not to be confused with a Kubernetes service. The Knative service is a top-level entity that manages a set of routes and configurations. Now you may ask, how difficult is it to migrate a Kubernetes workload to a Knative service? Let's have a look. So on the left-hand side, you see a Kubernetes deployment YAML. So this is a deployment. It has a name called front end. We specify a label selector and how many replicas we want. And then we specify the template for the pods that we want to spawn, which contains the same labels we just defined in the label selector, just to connect both parts of the YAML configuration. And then we define the container that we want to run. On the other hand, you see what the YAML would look like if we migrate that application into a Knative service now. Note that all I needed to change is the API version and the kind highlighted in red to move to a Knative service deployment, which is very handy if you already have an application built on Kubernetes and want to migrate that to a serverless architecture. I also do not need the parts highlighted in yellow. We can remove replicas and label selectors because that is handled for us in Knative. So we already have a more compact YAML file. But note that a Kubernetes deployment object is not enough to have a working application. You still need to define a service and an autoscaler to make that application cater to high traffic requests. While on the Knative side, that is all handled for us out of the box. So really, a simple yet powerful deployment framework that is very easy to migrate to from a Kubernetes deployment. Remember, we said two components, so we looked at the Knative serving. Now let's take a look at Knative eventing, the second component. Knative eventing provides the tools that allow us to route events from producers to consumers. Those events are based on the CNCF standard called Cloud Events, which defines a common format for events that can be understood by heterogeneous systems. The simplest eventing pattern is a source-to-sink pattern. An event source is an adapter for integrating external event producers with event consumers or sinks. The event source transforms events from the external systems into a cloud event before pushing them onto the sink, which is typically a Knative service. A Knative service, as you remember, manages the configuration and routes of our serving component. The source to sink is a simple pattern with some obvious drawbacks. For example, there are no queuing or filtering capabilities, and this pattern can only support one sink at a time. A more flexible and powerful pattern is the broker and trigger pattern. Here, the event source uses the broker as a sink, meaning it becomes the target of our event. The broker then will take those events and dispatch them to all sinks which are interested in this specific event type. To express interest in an event, a sink subscribes to a broker via triggers. And the trigger itself can have a filter expression that allows us to dispatch only certain events to our sinks. So with this setup, we can dispatch and filter events to any number of sinks. OpenShift Serverless, which is what we'll use in today's demo, is based on the Knative project. It packages all the goodness that comes with the Knative project in an enterprise solution that is supported by Red Hat. Now, before we jump into our demo, let's spend a few minutes to explain the context. So the industry we chose for today's demo is the gaming industry, not just because it's an industry that's dear and near to my heart, but more importantly, last year their revenue from the gaming industry exceeded that of sports and movie industries combined together, which just shows you how powerful the gaming industry really is. So what can disrupt this industry? Cheating. Game cheating has a huge impact on the gaming industry. A survey showed that 77% of impacted players are likely to quit a game if they have a negative experience against cheaters. And obviously those players are less likely to buy in-game content, so there's a real economic impact on the gaming industry. With that in mind, let's see together how streams and serverless can help protect our players from cheating. And the game we are going to protect today is Battleship. Our game is going to generate events that are written to a Kafka stream, and the rest of our components will run on a dedicated OpenShift environment. To those of you who have not heard of OpenShift, OpenShift is the enterprise version delivered from Red Hat on top of the Kubernetes project. So Kubernetes is the upstream project for OpenShift. So that OpenShift dedicated cluster is going to be linked to the Kafka cluster that is running on OpenShift Serverless. An audit service running on OpenShift cluster as a serverless function, and the audit service analyzes the events coming from our game and identifies and flags suspicious events. For simplicity, we have set a rule to flag an event for cheating if it contains more than 10 hits. A Kafka event source reads the events from Kafka topics and then forwards them to the audit service. The audit service will then emit a new event if it suspects a player is cheating, and this new event is routed to an email serverless function that notifies game admins about the suspected cheater through a broker and trigger pattern, just like the one we described. And I'll start now the video for our demo. As we mentioned, it's pre-recorded.
Okay, before we start, let's take a look at the prerequisites for the demo. And you can check this Git repo for all the steps you need to reproduce the demo using the Split.ly link, so shipOrs cheat detection. And what we'll need is access to the Red Hat console and access to the OpenShift developer sandbox. And then we'll need to install 3 command lines, the CLI for OpenShift itself, and the Red Hat OpenShift application services CLI, and the one for JQ, and JQ will make it much easier for us to extract data from a JSON file. And finally, I'm using SendGrid as my email platform. Okay, the first thing we want to do is head to the OpenShift Streams console, and OpenShift Streams gives you access to hosted and managed Apache Kafka clusters. I'm going to use here a limited trial instance, which will remain available for 48 hours. Now, let's create this Kafka instance and give it a name, like ship wars heat detection. And let's select a region and create our instance. You can see creation is now in progress. Once the Kafka instance is created, we now want to link that instance with our OpenShift environment. So I'm going to head over to my OpenShift developer sandbox environment, choose add from the side menu, then scroll down to the manage services option. I'm going to select my Red Hat OpenShift streams for Apache Kafka. Connect. We want to connect to our Kafka instance that we created on OpenShift streams. Once I select next, we're going to see that Kafka instance in our topology view. Also, a service account was created for that purpose, but we still need to grant the service account permissions to allow it to produce or consume events from our topic on the Kafka instance. So I'm going to get the service account ID from an OpenShift secret and store it in an environment variable. And then I'm going to log into my OpenShift streams account. Select the Kafka instance we created at the start of this demo. I'm now going to create a topic called shots. And finally, assign permissions to my service account. Looking back at our design, if you remember, our serverless audit service used a broker to emit events that contain the audit results, and then downstream services like the email service can register their interest in those events using a trigger and process them. So the next step is to create our broker. Now, if I go to my topology view and move to the administrative perspective, there is an option for serverless, and it's divided into serving and eventing, like we discussed earlier. And so if I go to eventing and then brokers, create a new broker from a YAML view, and I'm going to paste simple YAML that we will use for this purpose. And then create the broker. Now, if I go back to my topology view, we will see that the broker is indeed created. Now, the next step is to deploy my serverless functions, and we can obviously do that from my developer perspective. So I can click Add and paste the image name here. We can select a serverless deployment option, which also allows us to configure the scaling rules. So things like the minimum number of pods, obviously we want that to be 0. So when the service is idle, we can scale back to 0. And the maximum number of pods we want to allow our service to scale up to. The maximum number of concurrent HTTP requests we want to allow for our instance, and the utilization that we will allow before we scale another pod. This is one option, but what I'm going to do here is apply my configuration using YAML files. Here's the audit service. And then the email alert service. This will spin up two services in my topology view. As you can see here, the cheat detecting service and the audit service. Now, if we look at our architecture from the slides one more time, the next piece of the puzzle is the event source. So let's go ahead and create it. We select add from the side menu, and we went to add an event source, specifically a Kafka source. I'm going to click create. And here we have a nice wizard to help us provide the input. I'll first provide the Bootstrap server. This is the linked Kafka cluster we created earlier. Then I will add a topic called shots. I want to receive data from this topic. And our consumer group is called Knative Consumer. We also want to enable SASL. So this is where we use our service account details. Provide our client ID and our key. We also need to enable TLS. And finally, we want to direct the events from our shots Kafka topics to our cheat detection service. And we go ahead and create our Kafka source. As we expect, we will see that being created in our topology view on OpenShift. And finally, I'm going to create the triggers using a YAML file, which, as expected, immediately gets reflected in our topology view. Now, instead of actually playing the game, I'm going to simulate traffic with an application we created just for this purpose. Now, as you can see, my service, my other service, starting to scale up in response to the requests, and it's looking for a cheat rule. Here, we've set up the rule to look for a number of hits that's unrealistic. So a player using 10 hits at a time, for example, and then it's going to trigger an email notification. And that's exactly what happened. So the audit service detected that the player made 23 shots at a time, which is considered as cheating, and it invoked the email notification service, which then sent this email to my account. And as you can expect from a serverless architecture, my application starts to scale down once it becomes idle. So we've seen an end-to-end architecture where we've leveraged both streams and a serverless architecture to implement a cheat detection